So, now that we've talked about the Jacobian, how does substitution work? First we give a summary, and then we'll clarify. So suppose a transformation, and we'll just name the transformation, say capital T, but it really consists of x is being written in terms of two variables u and v, so described by a function g of input variables u and v, and y is equal to h of uv. If you have that set up as a transformation, as we have had in some examples we've already looked at, just to compute the Jacobian, and let's say that this transformation has region R in the xy plane. So this doesn't make much sense so far, the sentence as written so far. But there's a region called R in the xy plane. And this corresponds to, or corresponding to, let's also put the other word here, corresponding or maps, either word is fine, to a set S in the UV plane. Then the double integral over R of f of x comma y dx dy is going to become the double integral over a new region S. So this is like updating the bounds. It's a new region, new space of integration here. F of, replace the x here with g of u comma v. So f of g of u comma v, and then after the comma here, right there, y gets replaced with h of u comma v, and then we'll have here the Jacobian. So partial of x and y with respect to u and v, du dv. Okay, so there is substitution in a nutshell. This is probably not quite enough information to go off of when really trying to do this. So very more practically, let's lay out the steps a little bit more. To substitute, given double integral over the region R of f of x comma y dx dy. What do you need to do? Okay, so we're going to write this down as a multi-step process. So first off, choose a transformation. Yeah, choose a transformation. That is, in other words, write u. So what you typically do is when you first choose the transformation, you write this as u equals something here, and this is in terms of x and y. Okay, just on a practical level, it looks already a little different from here. I get that. We're going to clarify some things in a second. And same thing, you write v as some formula, and this formula is in terms of x and y. Okay, so do that first. There's a question of how do you choose a transformation? We're going to postpone that question still for a moment. So how to choose? This is like u substitution in the past, right? So in the past it was, how did you know u equals whatever? It was probably what you asked in calculus class. We're going to mostly leave out a discussion of this for now and come back to it, but we'll just say that you might need to you might need to sketch this. So you're given that integral, so you might need to sketch R to choose u and v well. Okay, I'm going to say that back in substitution for a single integral, often you got so used to when u substitution works and you kind of figured it out, and it was a very symbolic process. The fact that you may need to sketch means that the process is not going to be just very algebra-like. It's going to be much more geometric intense. I mean, there will be algebra, don't get me wrong, but it's not algebra alone anymore. Like, very much like everything else with double integrals and triple integrals, you will need to bring in the geometry into the story. If you try to do this process without doing any geometry, it will probably not work out very well. Step 2, and then here's step 2 is what's going to bring it into this fashion of x equals a formula with u and y equals a formula with u and v as well. So what we'll do is we'll solve for x and y. Yeah, solve for x and y in terms of u and v. Step 3, based on the transformation, based on the transformation that was chosen in step 1, describe the region S in the UV plane corresponding to the region R, which was in the XY plane. Now, I can't stress this enough. This step here is highly geometric. You have to think about geometry. Step 4. Then write f of g of u comma v comma h of u comma v. The work from step 2 is going to be helpful. Okay, write this out. Use the work from step 2. After all, in step 2, you solve for x and y. So at the end of step 2, the result is you've got x is equal to something that involves u and v, and you've got y is equal to something that involves u and v. So step 4 is actually not a lot of work if you've done step 2. And then step 5, also based on step 2, compute the Jacobian. So compute the partial derivative of both x and y with respect to both u and v. And then step 6, set up that the original double integral, okay, the double integral over r of f of x comma y dx dy. Yeah, so this was the old integral. Instead of computing the old integral directly, because we're choosing to do substitution, we're going to have the double integral over region S, so S comes from step 3, of f of g of u comma v comma h of u comma v. And so this part here comes from step 4. And then we had the Jacobian, so partial derivative of x and y with respect to u and v. And so this comes from step 5. And then you just need to write here a du dv. Okay, and just leave this alone. Just copy that there. Right, because your integral should end with a d something and a d something.